Okay, welcome back to another session. So please, before we begin, do you have any questions for me? Any comments? Any issues? Oh, and before we move on, I hope you've already seen that I've posted your grades for the exam that you took on Friday, right? If you see any errors, like if you think you were some points were unfairly deducted or anything, please draw my attention as soon as possible. I'll try and rectify that and award your points, right? Yeah, so that's the statement on that. Okay. Any questions or comments? Okay, let me also encourage you that at this point, you've already taken 2 exams, right? But keep working very hard, because the thing is, even if one of the exams didn't go so well, you can replace one of your midterm scores with your final grade, right? So it's possible for someone to not do well on one of them, and then all of a sudden get a very good grade on the final, and then shoot up like in grade, right? So keep working hard, try and do well on the 3rd exam, and then the final 2, and it should still be good. Okay, so let's move on to the lesson, right? I'm sharing my screen now. Oh, and one more thing. So encouraging those who may not have the grade they want at the moment. And then this also goes to those who also have it at the moment. It's possible to still falter if you relax, right? Because if you feel like the 3rd exam, it's almost as if you failed one of the exams, the earlier ones. So still keep working at, even if you are doing so well or you are not doing so well, right? Keep going, right? And if you need help, please seek it as soon as possible. Don't wait for it to pile up, right? Okay, so that's it. Now let's move on. So I'm sharing my screen now. If you can't see, do let me know. Okay, so last week, right, we introduced differentials, and we said differentials are used to what? To get an approximation of a natural true change in y, in the dependent variable, right? So if you want the true change in y, right, which is denoted by delta, say y, where's that notation? Yeah, delta y, I think it's here. Yeah, this delta y, right? Then you can approximate this delta y using what? The differential dy, right? So that's the statement we made the last time. Now we saw an example where I was able to demonstrate that the dy, the differential dy, is actually close to the delta y, the true change, right? So for example, for this first one, we got the true change to be this, and then the delta y is what? 0.7. These are quite close, right? This one also, the true change is 0.140701, and then the delta y is what? 0.14. In either case, the differential can be used as what? An approximation. It's kind of like a linear approximation to the true change. So with this approximation that we do, usually with approximations, when you do them, it's always a good idea to get a sense of the error that occurs when you make that approximation, right? So after making that approximation, which kind of errors are you getting? Is the error very, very huge or what, right? So this is what the final example is going to talk about. So that's example 4. So for example 4, we are told the radius of a sphere was measured and found to be 21 centimeters with a possible error in measurement of at most 0.05 centimeters. What is the maximum error in using this value of the radius to compute the volume of the sphere, right? So let's gather the information from here. Now, from here, you're given this 21 centimeters. So the radius of a sphere is measured to be found. So this is it, right? So this is the radius. So let's call R the radius, right? Now, because the R is the radius, we said that when we're measuring the volume, right, we may have, when we're measuring the radius, we may have made a possible error in measurement of what? 0.05, right, in measuring the radius. So that error in measurement in the radius is dr, right? Because the radius was supposed to be some true value, and then we measured it wrongly. So the dr, which represents the change in the radius from a point to another point, represents the error, because this is this is the true value, right? And then we estimated using this. So we've made an error of what? The difference. The difference will give you the error. And then the difference is denoted by dr. So that is what? 0.05. Right. So now that you have the differential, what the question is asking about is, it says, what is the maximum error in using this value of the radius to compute the volume of the sphere? So we are actually interested in what? This, the delta V, where V is volume. Volume of sphere, right? This is our volume of a sphere. So this is what we are trying to get precisely. But as we said, for this one, we are trying to approximate this value using what? Differentials. So that means for this one, the equivalent differential which will be used to approximate this is dV, right? So let me say this is approximately delta V. So you'll be working with the differential dV rather, you see. So let's work with that and then see what you're going to get. Now for this problem, one other important thing you have to know is what is the volume of a sphere, right? What is the volume of a sphere? So let me go to the whiteboard. Now, volume of a sphere is given by 4/3 pi r cubed, like so, right? So if you want the differential dV, what do? Well, you do dV, the independent variable here is a radius. So dV over dr equal to what? D over dr of 4/3 pi r cubed. And then we get dV over dr equal to, now you can pull out a 4/3 pi since it's a constant, right? And then you have the d over dr of r cubed. And then that one is just 3, but the power is 3r squared. So we get dV over dr equal to 4/3 pi times 3r squared. But then we are trying to solve for the differential dV, right? So you multiply both sides by dr, so you get what? And then the 3 cancels out here. So you get 4 pi r squared and then dr. So this is a differential dV, right? This is a differential. Now, with this given differential, this differential represents the what? This is an approximation of the what? The maximum error in measurement of the volume, right? So that's it. We are going to use this to approximate that error in measurement of the volume, right? Okay, so that's the maximum error. Now we have the values R to be 21. We have the R to be equal to 0.05, right? This in centimeters. And then, yeah, so let's get dV. So dV will be equal to 4 pi, R is 21, all squared. And then the R is what? 0.05. So crunch these numbers, and then you get dV to be equal to, okay, it's approximately 277, right? 277, it's approximately 277 centimeter cube. So this represents the what? The maximum error in measurement of the volume. Is the approximate value, right, of the maximum error in measurement of the volume. Please, any questions on this? Okay, so this is one way we can get it, the error, right? You can get it directly, right? The maximum error that you want to obtain. Now, with this error, right, sometimes it's difficult to compare in between units, right? So suppose I have a measurement, right? And then I use, say, pounds and I use some kilograms, right? I say, let's say there's an error in measurement of, say, 27 pounds, an error in measurement of, say, some other unit. Or let me use a unit which you can easily compare. Let's say pounds and centimeters, right? How do you decide which error is bigger between the two, right? So what we do is we use a unitless comparison. What I mean by unitless comparison is these two. We are going to talk about two other errors that we can use. The first one is called a relative error, right? So instead of getting the actual unit, you're going to use something which is unitless to get an idea of the error so that you can easily compare errors without necessarily thinking about what kind of units that they have, right? So the relative error, what is relative error? Now, to define what the relative error is, you're going to talk about the example that we are dealing with here and talk about its relative error. So for this question, we are going to compute the relative error of the volume, right? The measurement in the volume. Now, the relative error is just going to be the what? The change, right? The error made in the volume measurement over the true volume. But because you're using the differential to approximate this delta V here, this is just the relative error can be estimated using the differential over the true volume, right? So we are just dividing over the quantity that we got the error in, the error measurement in, right? So if you say you are doing an error in measurement in the area, then it will just be say, and then the A is area, then it will just be say the A over A, right? So it's always going to be the differential of the quantity over the quantity itself, right? So now that we have the V and then we have the volume, let's just plug everything in there and then see what the relative error is. And this one will be unitless, right? So the V is 4 pi r squared, the R. And then volume is 4 over 3 pi r cubed, like so. And then when you get here, you can cancel out, right? Just reduce. So this cancels this, pi cancels pi. And then r squared cancels one of the r cubes here, leaving us r. So you put everything together, you get the, what's up there? The r over 3, right? And then that simplifies to the r divided by r over 3, that's 3 the r over r, right? But then we have the r, we have r, right? The r is given by 0.05 centimeters, and then r is 21. So we can plug these numbers in there. And then crunch these numbers, and you get your relative error. So I'm going to have to do that on the next slide. So please do let me know if you need more time. Let me see. Okay, 1 sec. Sure. Done. Okay. Okay, cool. You're welcome. So moving forward, we have the relative error in the volume measurement given by what? So the relative error in the measurement of the volume is approximately, when you crunch the numbers, you're going to get something like 0.007. Right, so this is a relative error. And you see it's unitless. It doesn't have any units. Right, it's unitless. Now, in the same sense that we got a relative error for the volume, you can also get a relative error for the radius. Can anyone suggest what the formula will be? What will be the relative error for the radius? Anybody? What will be the relative error for the radius? What do you think? How do we compute that? Anybody? Remember, the relative error for volume is just differential volume over the volume. So what's the relative error for radius? Anybody? Perfect, perfect. Thank you. It's just going to be the differential of the radius over the radius itself, right? Is that, yeah, just like that. So the differential of the radius is 0.05, then the radius is 21. So that'll give you approximately 0.0024. Yeah, that's all. Right, so that's relative error. Now, another kind of error measurement we can consider is something we call a percentage error. So for percentage error, it's just the relative error times 100%. It's just relative error times 100%. So in that case, you're looking at percentage-wise, right, of the relative error. So let's consider the percentage error of the volume, right, and then the percentage error in the radius. So for the volume, if you want the percentage error for the volume, the percentage error will be given by the V over V times 100%. So it's essentially what we got, right? So previously for the relative, we got 0.007. So it's just 0.007 times what? 100%, which will give us a percentage error of what? So 1, 2, 0.7%. That's a percentage error in the volume. If you want a percentage error in the radius, right? The radius, then the percentage error is just going to be the R over R times 100%, right? And that's just going to be the d over R, you got 0.0024, and then times what? 100%, times 100%. So that just be 1, 2. So that'd be 0.24%. So that's also the percentage error for the radius. So these are some errors that we see when we use the differentials to measure, right? Or we use approximation to obtain the results of the true error. Okay, now any questions here? So that's it for 3.10. Anybody needs time here? You need more time. Okay, then let's go to the PowerPoint slide, right? So just to show you, the solutions are already here, like they have 9 notes, right? So yeah, this is a percentage error. Okay, so let's move on to 4. Right, so now we are here on a fresh start. So the exam 3, right, is going to be on 4.1 to 4.9. So this is like a fresh start, right? A fresh start. So now let's start with 4.4. For this one, I think I'll define. Let me switch between this and this. I'm sharing the PowerPoint. If you can't see, do let me know. So 4.1, we're going to look at maximum and minimum values. Maximum and minimum values. Now, when I get to the end, I'll summarize all that you need to know. Here, because we started a new section, I'm going to define a lot of things, right? But I'll summarize the ideas you have to know, right? Okay. Now, you notice that the calculus that we do, a lot of it is used in optimization. That's why it cuts across all fields, right? Because people optimize wherever they are. Like if you're doing, say, material engineering, you have to optimize the material that you have and then how you're going to use it to construct like cost. You have to check the cost and then the material, like maybe purchase at a lesser cost, and so that you develop something you can sell and then get more money, right? So you optimize wherever you are. So the ideas of optimization are in maximization and not minimization. So we are just going to consider looking at the minimum and the maximum values of a function, right? So let's consider the first graph, right? The first function. So for this first function, the question is, what are some of the features that you see on this function? Well, one important feature I can see here is this function is defined between this point and that point here, right? That's the first thing. But then between that interval, I notice that this point right here is the highest point, right? Is the highest point on the entire graph. In other words, this value you see here, which is 5, is the biggest value on the function, right? Is the biggest function value, is the highest point. Now, other thing you see is in terms of maximum values and minimum, this point here at 6, right, which will be 2, is the what? Is the smallest number, right, of the function. The 2 is the smallest number, and it occurs at 6. For this one, the 5 is the largest number, and it occurs at 3, right? So please note the words I'm using, right? It occurs at 3, but if the question asks you for the value of the function, the value of the function is the y coordinate values, right? So the value is 5, it occurs at 3. The value is 2, it occurs at 6. Now, we define the concept of absolute maximum and absolute minimum. Now, just as you saw the graph on this previous slide, on slide 4, you notice that this value that you see here is the biggest value on the entire function. And then this value you see here is the smallest value on the entire function. So that means that just as we saw in the previous example, we can say that the value 5 is an absolute maximum value of the function, right? It's the absolute maximum value. Why? It's absolute. There's no other number which is greater than that, right? So that's why it's absolute. On the other hand, we can also refer to what this 2, the value 2 here, as the absolute minimum value of the function, right? Now, note that as I was saying, the absolute maximum value for the example that we looked at is 5, but it occurs at 3. So please note the distinction between them, right? Sometimes a question may ask you where it occurs at, and on another case, it will ask you what it is, right? So if it asks you for what the value is, then it's the y coordinate. If it asks you for where it occurs at, then please is the x coordinate, right? So just note the difference. Okay, so now let's formally define what an absolute maximum and minimum values, what absolute maximum and minimum values are, right? So let's C be a number in the domain of D. So first and foremost, this C has to be in the domain of the function, right? Then f of C is, you see, so f of C, so here is considering the y coordinate. F of C is the absolute maximum value if this point is greater than or equal to any other point of x in the domain, right? So there's no point which is going to be above it. The best possible cases, you can have an absolute maximum value being equal to, like being the same, but occurring at several points. So that's why it says f of C is greater than or equal to. Or equal to part means that you can have the absolute maximum value occurring at several points, but there is no other point which will be higher than that point, right? So that's absolute maximum. Now for absolute minimum, it's just the opposite, right? So this time around, we're looking at what? The value of the function such that it's less than or equal to any other point. So there's no other point which is going to be below it. The other case scenario is you can have the absolute minimum occurring at several x points, but there's no point which is going to be beneath it, right? So that's absolute minimum. Now the absolute maximum and minimum are also sometimes called global, right? Global maximum or minimum. And then in general, minimum and maximum values are also referred to as extreme values. So just note these, the diction here. You'll be interchanging between them. But I think I'll stick more with absolute and absolute max and absolute minimum. Please, any questions on the definition? Anybody needs time here? Okay. So now let's look at this graph, right? And then try and get some more information on maximum and minimum values. Now, looking at this graph, we just introduced the concept of absolute maximum, right? And then absolute minimum. Now, you can see that for this graph, right, this point here is the highest point. So I can say the absolute maximum. I'll denote the absolute by ABS and then dot, right? The maximum value is what? F of D, right? Is the highest point, and no other point on the curve is higher than that point. Okay. Now, what about this point? Now you can see here that this one is also the lowest point, right? The lowest point. So I can say my absolute minimum. My absolute minimum value is what? Is f of A. Because this point here is the lowest point on the entire curve, right? So we've been able to identify our absolute maximum, absolute minimum. Now, let's introduce some other new concept. You can see that the graph sometimes, like say, reaches a smaller point within the, like when you look at the graph, right? When you look at the graph, say along the line, right? You see that sometimes the graph could be smaller within some range or higher within some range, right? What I mean by within some range is when you just fix an open interval on the function, sometimes the function could be higher than any other point in that open interval, or it could be lower than any other point in that open interval. So in that sense, you can think of it like a local something. Say in normal sport, right? You can have a local champion. Now, what do you mean by a local champion? A local champion is like, let's say within some vicinity, that person is like, say, the best at what they do, right? Within some vicinity, local, right? So the vicinity thing in the math concept, translating this to math, we are talking about local if we are able to fix an open interval which contains the point such that that point is, say, higher than any other point, in which case we refer to it as a local maximum. Or that point is what? Within that open interval is smaller than any other point in the open interval, in which case we call it a local minimum, right? So looking at this graph, right, you can see that for the point B, if we restrict this point B in this open interval, well, the function is defined for that open interval. And it turns out that this point B here is higher than any other point in that open interval, right? So that means that the point B f of b, right, is a local maximum. That's why you see LOC max. So that's a local maximum value, right? Now, moving along, you can see that for this one too, for C, we can restrict C in some open interval. The function will be defined in that open interval, right? And then this point C here is smaller than any other point within this interval. So we can say, oh, okay, so f of C is also a local minimum value. It's a minimum value, but it's in a local region. It's not global. Okay, now let's move forward. Now, this point here is an interesting one because we've already identified this to be an absolute maximum, right? Occurring there. There's an absolute maximum value there, which is f of d. But the thing is, just as we did for B and C, we can also restrict D in an interval such that this point here is larger than any other point in that interval. So just as this is an absolute maximum value, in this case, it is also a local maximum value. You can think of it like in sport. In sport, it is possible that someone who is in, say, your locality might be the world champion, like the entire champion. The person is a champion in the locality and is also champion amongst all the champions, right? So this one, in this case, we can restrict it in the open interval such that this absolute maximum value, or this big value, this number here, is also higher than any other point within that restricted open interval. So this is both an absolute maximum value and a local maximum value. Right, that's why you see this listed here, f of d, as a local maximum. Now, moving forward with this, I'll come back to this absolute minimum, right? Considering this one, I'll come back. Now, moving on, you can see at this point to E, we can restrict it in an open interval such that this f of E here is less than any other point here in this interval. So we can say that the f of E is also what? A local minimum value, right? So it occurs at E, right? F of E is a local minimum value. Please, I hope you understand this. Now, the question is, are all absolute mass or minimums going to be local mass or minimums? Well, don't forget that the key to getting a local either maximum or minimum is that the function has to be defined in an open interval which contains that point. But the question is, looking at this point, A, we all know it's an absolute minimum, right? The f of A is an absolute minimum value. But the question is, can we put A in an open interval? No, the function is defined for this side, for the right of A, but it's not defined for the left of A. So that means that the point A cannot be put in an open interval which will contain the function, where the function will be defined. So this one is not, this absolute minimum value is not a local minimum value. You see, in this case, this one is not a local minimum, but it is an absolute minimum value. Please, are you okay on that? I hope you understand this. So the key is, in defining a local, you have to be able to restrict that point in an open interval, such that the function is defined across that open interval. Please, any questions here? Anybody needs time here? Okay. Now, this is just the formal definition of a local maximum or minimum. So this one is saying the number f of c, right, is a local minimum value of the function if the f of c is greater than or equal to f of x when s is near c. So this one is actually similar to this definition. But this one, the only difference is this one says for all s in the domain. For this one says when x is near c. Near c means we can put it in some, you can put that c in some open interval containing c, right? You have to be able to put it in an open interval such that the function is defined on that open interval. Then when that point c is bigger than any other point in that open interval, then we say we have a local maximum value at that point. Okay, now in the same sense too, we have a local minimum value of f, right? F of c is the local minimum value if f of c is less than or equal to f of x when x is also near c, right? Yeah, and that's a local maximum and local minimum. Is any questions here? Okay, so let's do more stuff on this absolute and local mass or mean values. So for this one, let's consider this graph. So for fig 3, right, you can see that it says f of 4, which is equal to 5, right? So f of 4. So this one is a good illustration of the locale. So you see that the open interval has been colored in like a rectangular blue, what you see here, right? So this point here, if we are able to restrict the 4 in some open interval, the function will be defined in that open interval, such that this point 4 here is less than what any other point in that interval. So that means that f of 4 is a local, what? F of 4, which is 5, is a local minimum value. Now moving along, you can also see that for this point here, right? For this point here, if you restrict it in an open interval, then this point is higher than any other point in that locality, right? So we can also suggest that f of it occurs at 8. So there's a local minimum value at 8, and the value is this one. When you read it somewhere, I think 7. Yeah. So a local maximum value. Now, what about this one? Now, for this one too, at 12, you can see that we can restrict the function in an open interval. The function will be defined within that open interval. And this point here will be smaller than any other point in that open interval, right? So that means you can say f of 12, which is somewhere 3, right, is a local minimum value. But the thing is, for this point, right, you can also see that along the entire graph, there's no other point which is lesser than this point. So that's why this 3 is both a local minimum value and an absolute minimum value. Now, this maximum you see here is not an absolute maximum, because when you trace this, you see that there are other parts of the curve which are higher than that point. So it's not an absolute maximum. Please, are we clear on this? I hope you understand the definitions. Any questions? Anybody needs time here? Okay. Then let's proceed. Okay, so this is just talking about what I said, right? So it's not an absolute minimum because, so it's talking about the first one, the value at 4. It's not an absolute minimum, right? Because S takes smaller values. And this one is a local minimum and an absolute minimum. That's the one we talked about. And then the F of 8 is a local maximum, but not an absolute maximum because F takes larger values near 1. Okay, now let's proceed. Let's look at the another one, example 1. So for this one, let's consider the trigonometric function cosine. Now, as you can see, for cosine, it oscillates between -1 and 1, right? Infinitely, right? So the highest point it can achieve is at 1, and then the lowest point it can achieve is at -1. Now, this also, the function is defined for all real numbers. So that means that at any part where you have a local maximum, local minimum, you can have a local maximum or local minimum because you can restrict the function in some open interval and the function will be defined within that open interval, right? So in that sense, the one that you see will occur at infinitely many points. So for a cosine of x function, the absolute maximum value is 1, and then the local maximum value is also 1, right? In the same case, the absolute minimum value is -1, and the local minimum value is also -1. But the only difference between this and some of the functions we've seen earlier on is, for this one, the absolute maximum value occurs at infinitely many points, and so does the local maximum value or local minimum value. You see? Yeah, so that's it on this. Please, any questions here? So this is just illustrating that you can have an absolute maximum occurring at several points. So here it occurs at 0, it occurs at 2 pi, the local maximum occurs at 0, 2 pi. And so with the look at the absolute minimum. What did I say local? I meant for the absolute values, you can have them occurring at several points, right? So absolute maximum is what? 1, and it occurs at several points, 0, 2 pi, and so on and so forth, 4 pi, 6 pi, and so on, right? And then the absolute minimum also can occur at several points. So that's why for this one, it occurs at pi, 3 pi, and all the odd pi's, like 5 pi, 7 pi, 9 pi. and so on. Okay, any questions so far? Okay. Now, let's proceed to this theorem, right? Let's proceed to this theorem. Now, the thing is, when are we guaranteed to have an absolute maximum and an absolute minimum? Now, the guarantee lies in this theorem. This theorem says if the function is continuous, right? So two things. If the function is continuous and on a closed interval, right? So if the function is defined on a closed interval and it is continuous, then f attains an absolute maximum value, f of c, and an absolute minimum value, f of d, at some number c and d in the interval, in the closed interval a to b, right? So two conditions. If the function is continuous and the function is defined in the closed interval, then there has to be what? An absolute maximum and an absolute minimum, which will occur at either the endpoints or in between the points, in between the endpoints. So that's the extreme value theorem. Now, the proof of this theorem is beyond this class, but we are going to show examples which illustrates this, right? Which illustrates the extreme value theorem. So let's look at the first three, right? So for the first one, the question is the function continuous? Yes, the function is continuous. Okay. Is the function defined on a closed interval? Yeah, the function is defined on some closed interval a and b. You see the dotted point here, right? So that illustrates that the b it can be read as part of the function, and you can read the value for a2. Now the question is, considering just this graph, do you think that the function is what? Has an absolute maximum and the function has an absolute minimum? Well, let's see. Well, I can see that this point here, this point here is higher than any other point on the graph. So the f of c is the what? Is the absolute maximum. So that means I've been able to obtain an absolute maximum here. Now, looking at this point also, this point is the smallest, has the smallest value of the function on the entire graph, right? So the f of d is what? Is my absolute minimum, right? My absolute minimum value. So yeah, I was able to obtain an absolute maximum and an absolute minimum, right? The function was continuous and defined on a closed interval, and the extreme value theorem worked. Okay, now let's see. Let's try and change things a bit. This time around, we are just considering this graph, and it's also defined. So the function is continuous, defined on a closed interval. The question is, will the extreme value theorem still hold? Well, for this function, you can see that this point C here is the highest point, right? So this is going to be my absolute maximum value. On this time, on this one, right? Unlike the previous example where we had the absolute minimum occurring in between the A and B, for this one, you can see that at the end point, that's where we get the absolute minimum. You see, this point is smaller than any other point here, right? So this is what? The f of d is my what? Is the same as the f of b. And that's what's going to give me my absolute minimum value. So the extreme value theorem still holds, right? As long as the function is continuous and defined in the closed interval, it must have an absolute minimum and an absolute maximum. So these examples don't contradict, right? Let's do more. Let's look at the last one. For this last one, the function shape has changed, but the key is the function continuous and is it defined on a closed interval? Yeah, this function is continuous and it is defined on a closed interval. Let's see if the extreme value theorem still will hold here. Are we going to have an absolute maximum and an absolute minimum? Well, as you can see, this point here is smaller than any other point. So the f of d is what? Is the absolute minimum value, right? Now, another thing we can see here is at C1 and C2, these are the same points, right? They read the same value. So that means that for this one, we have the absolute maximum value, okay? So the absolute maximum value occurs at C1 and C2, right? So absolute maximum value. So the extreme value theorem still holds, right? So what we are trying to say is we've not been able to disprove this, right? As long as the function is continuous and defined on a closed interval, the extreme value theorem will hold, which says that what? There has to be an absolute maximum or an absolute minimum, which will occur at either the endpoints or in between the endpoints. Please, any questions on these definitions? Anybody needs time here? Okay, now let's look at these two examples. The question is, do they contradict the extreme value theorem? Well, let's look at the first one. Now for the first one, don't forget that for the extreme value theory to hold, the function has to be continuous and what? Defined on a closed interval. Okay, let me see if I'll get an absolute maximum or an absolute minimum here. Okay, so now for this one, oh, nice. I have an absolute minimum here. It occurs on the x-axis, so it's 0. But the question is, can I get an absolute maximum value on this? Can I get an absolute maximum value? Well, as you can see, the function, the highest point is attained somewhere here. 3, this one is a point show. So that means the function is never 3. But the thing is, can we get an absolute maximum here? Don't forget, between even 2.9 and 3, there are infinitely many values, because 2.9 and 3, between 2.9 and 3, you have 2.99, 2.999, 2.99999, and so many nines you can say. There are infinitely many numbers. So if the 3 is not attained, and then the function is getting close, you can't tell which exact value the function is taking. In other words, you can't tell the absolute maximum value. So for this one, there's no absolute maximum value. Please, I hope you understand this. Right? Because the function doesn't take on 3, and getting close to 3, there are infinitely many numbers. So it doesn't take on an exact number to make it an absolute maximum value. So this one has no absolute maximum value. But the thing is, does this violate the extreme value theorem? Has the extreme value theorem failed in this case? Well, the extreme value theorem says 2 conditions. The function has to be continuous, and the function has to be defined on a closed interval. Well, for this function, we can see that it's defined on a closed interval, right? But the function breaks up here. It's not continuous at this point. You call it, say, let's say 1. It looks like 1, right? The function is discontinuous at 1. So that means the extreme value theorem has not said anything. Well, so the extreme value theorem give two conditions. It said if the function is continuous and if the function is continuous and then the function is defined on a closed interval, then there has to be an absolute maximum value, right? But then in this case, you violated one of the conditions. So the extreme value theorem is like, now I give you 2, right? If you violate it, that's your own issue. If you violate it and you don't get an absolute value, then I said 2 conditions have to hold. So if one of them is not holding, then there are no guarantees. So in this case, the function is discontinuous, so there was no guarantee we are going to get an absolute maximum value. So the extreme value theorem is still correct, right? No violation. Okay, what about this one? The second one. So for this one, can we get an absolute maximum? Similar to what we had for the previous one, you can see the function is going up, right? You don't see the exact value it attains. It just goes up and up and up. So this one has no absolute maximum. And then for the minimum 2, you can see that the one at 1, we have a point show, but then the function keeps decreasing and decreasing. And as I said, between say even 0 and 0.1, there are infinitely many numbers. So the function is continually getting close to 1, but we don't know the exact value, which is like the final smallest value it attains, right? So this one also has no absolute minimum. But the question is, is the extreme value theorem wrong here? Okay, the extreme value theorem says 2 things. The function has to be continuous and the function has to be defined on a closed interval. As long as those 2 hold, then there has to be absolute maximum and absolute minimum here. Okay, so the question is, does this violate the extreme value theorem? Well, for one, you can see that even though the function is continuous, this function is not defined on a closed interval. It's not defined on a closed interval because you have a point to at 0, right? And then the function is also not taking on any values at 2. So that means the extreme value theorem is still correct. This does not violate the extreme value theorem. Okay, please, any questions on this? Okay, now the next slides are just going to explain what I just said, right? Okay, so does not contradict the extreme value theorem. Okay, so now let's try and start to find extreme value theorem. The question is, how do we obtain extreme value theorems if you have a function or say for that matter a graph? Now let's start with this graph, right? So for this function f of x, that's in blue. It shows you that we can start by finding extreme values by looking at the local looking at the local maximum or minimum, right? In other words, the turning points. That could be a start, because for the previous functions that we saw, we could see that, like for example, let me go back. for example, for this one, right? For these graphs, you can see that the extreme value, one of the extreme values happened at the turning point. This one, it also happened here, right? Which is also a local maximum. For this one too, it happened here, right? And previously too, you can see the extreme values happen here, which are also local extremes. So that's why this one is saying, when we are trying to figure out what extreme values are, it's a good idea to start with the local maximum, local minimum. All right, so let's look at the idea. Now, one of the mathematicians says, his name is Fermat. I think this guy used to do it for like as a hobby or something, and discover some of these theorems. Now, one other thing is for the local extreme values, or for the turning points, right? So we are looking at turning points. For turning points, you can see that the slope of the tangent is what? Is 0, right? At turning points. At turning points, the derivative is 0. So that means that will be a good start, right? So Fermat theorem says, Fermat, right, one of the French mathematicians, he says, if a function has a local maximum or minimum at C, and if f prime of C exists, then f prime of C is equal to 0. Okay, so note this. It says, if there is going to be a local maximum or a local minimum at C, and if f prime of C exists, then f prime of C equal to 0. Now, this theorem doesn't say that, it doesn't say that if there's an absolute maximum, it has to have f prime of C equal to 0. For one, it's possible that the function's derivative, the function is not differentiable. In previous sessions, we saw some functions which were not differentiable. That means if the function is not differentiable, this does not apply, right? It does not apply because you can't even get f prime of C in the first place. It's not defined, you see. So Fermat is saying that if the f prime is defined, right, it exists, then the f prime of C equal to 0 if there's a local maximum. So it's possible that there could be a local maximum, but then the f prime does not exist. But as long as there is a local maximum and f prime exists, then that f prime is 0, right? So just note the distinction between them. Now, this is just going to illustrate that, this example 5 illustrates that even though we are saying that if there's a local maximum, right? See, if there's a local maximum, and then the f prime exists, then the f prime of the local at that point is 0. But the fact that the f prime is 0 doesn't mean that there's a local maximum. So this illustrating this. Now, suppose we have the function s to the cube, right? You see this function often, right? So that's the function. The thing is, this point here, there is going to be a horizontal tangent. So that means that f prime of 0 is 0 at that point. But the question is there a local maximum or minimum here? No. When you restrict this in an open interval, so it's like this. When you restrict this in an open interval, this point here is neither a local max or min. Why? Because when you restrict this in an open interval, there are points which are smaller than this. So it's not a local minimum. And there are also points which are lighter. So it's not a local maximum. All that this is telling us is the f prime of the 0 is 0, right? There's a horizontal tangent at that point. So all that we're saying is, whenever you have, you start with a derivative, right? And then you find the values where the derivative is 0. There could be the points, amongst them, you can have points where you have a what? A local maximum. But you're not saying that all the points are going to have local maximums. So there are mixtures in there. You could have a possible case where the f prime of 0 is 0, but then at 0, there's no local maximum. But what we are saying is, if there's a local maximum, then the f prime of 0, and the f prime exists, then the f prime of 0 has to be what? 0. So the converse is not true, right? If it's local f prime and the f prime exists, then f prime of that point is 0. But the fact that f prime of that point is 0 doesn't mean it's a local maximum or minimum occurring there, right? So that's the first violation. One thing that you have to be concerned about when you're considering Fermat's theorem. Now, I'm explaining stuff, but I'll summarize what you need to know, right? We are moving on to develop something here. Okay, so this one is saying that the f prime being 0 just simply means that it has a horizontal tangent, right? Okay, but we don't have a maximum or minimum at that point. Now, another thing is, as I was saying earlier on, is sometimes it's possible to have a local maximum point. And if the f prime does not exist, it's still going to have a local maximum point. For example, when you look at the absolute value of x, at 0, you have a local minimum, right? This is a local minimum. A local minimum occurs here. Why? Because if you restrict this in an open interval, then the function is defined. And then this point is what? It's smaller than any other point. So it is what? We have a local minimum value, which is 0. But the thing is, for at 0, right, the f prime does not exist. The f prime does not exist. That means that it's possible that the derivative will not exist, but there can be a local minimum at that point. Right? So that means that when we are checking for local maximum or minimum values, we have to be careful. Oh, it's 1150. You have to be careful. We have to check. So let me conclude here. We have to make sure that sometimes the derivative might not exist, but then there could be a local maximum, or there could be points where the f prime is 0, but then there are no local extreme values happening there. Right? So there's a conclusion. So example 5 and 6 show that you must be careful when using Fermat's theorem. Example 5 demonstrates that even when f prime of c is 0, there need not be a maximum or minimum at c, right? And then there may be an extreme value when f prime of c does not exist. So that's the last slide for today. Thank you for your time. I think next time, yeah, we define critical numbers, which is what you have to know. Like that's one of the summaries. So you continue on slide 22 on Wednesday. Thank you. Feel free to reach out if you don't understand anything. Yeah, so all the best. I'll see you on Wednesday.
Thank you.
You're welcome, Shane. You're welcome, Camden. Let me